In this short video, I'm going to introduce us to the concepts of modern multi-layered computer systems. This includes the layering of hardware as well as software layers above it. We'll talk a bit about what the advantages are of doing such things and what are some of the consequences. To start, I want to look at two major programming models, at least as relates to our discussion. So not system programming versus object-oriented types of programming or procedural languages, that kind of thing. This is a little different. In the first model, which we'll call translation, we're going to write a software package in some kind of high-level language. Could be C++, could be Java, whatever it might be. And it does some human-level thing. So it could be accounting software. We write that in our first language, language 1. Then by passing it through a compiler or other such tool, we translate that human-level code down to another language, which we've got listed here as L2, which is effectively the machine language of a computer. Now that machine language is going to be a bunch of zeros and ones, and it'll effectively be the binary that runs on the bare metal of the machine. Now by separating those two things, by starting in a high-level language and then translating that into its equivalent machine language, we end up with the same functionality that we envisioned when we were thinking about accounting, but we were able to write the solution for our problem in a language that was much more suitable for the terms of accounting, rather than a machine language which is effectively there to instruct the machine to do very simple low-level things like add 1 to something. Right? So there's the basics of translation. In the second model, which we have here, is its interpretation. So again, we write some applications, say accounting software, in a high-level language like language 3. Instead of translating that language down to machine code, that textual source code is used as input to some kind of interpreter. You can also think of this as a virtual machine in another fashion. Right? Now the virtual machine itself is a program, but it's using the source code that we wrote in language 3 as input data. So our program really isn't a binary that executes on the computer at all, right? There's a layer in between us. Our program is written in a high-level language, and that text of our program is used as the input to the interpreter or the virtual machine. And it's the virtual machine that actually executes on the bare metal. So the virtual machine is the only thing that's running here, and by using our original program written in L3 as data, it changes its own performance, thereby effectively producing the same result as the application we described in L3. So it is interpreted. Now that interpreter probably, if it's running on the machine, it was written in some high-level language, could be a completely different language, L1 again perhaps, which was eventually translated down into machine language so that it could run here on the bare metal. All right, so we break up our devices, our computers, into a variety of layers. And what I've got listed here are the primary breakdown of layers from high level to low level. And this includes the hardware and software systems. So I'm going to start from the bottom and go up here. So, and that's the same way we're going to continue this presentation. At the very bottom is the digital logic layer, which deals directly with bits and gates. Above that, we have the microarchitecture layer, where we bring many elements of the digital logic layer together to do particular larger functions. Those are exposed through the instruction set to our programmers at low levels. And then operating systems come in to abstract all of that stuff away from us, at least as best as it can be done. And then we have the opportunity to write, say, user-level programs at the lowest levels in assembly language, but more likely in languages of higher level than that. At the digital logic layer, we're basically looking at what are called gates, a bunch of gates. So the digital logic layer of a computer is about the organization of individual logic gates to perform very, very small functions. In particular, these gates receive input signals that are binary, 0 or 1. And then while they may get in multiple signals, multiple inputs, they tend to produce single bit outputs, 0 or 1. Or we can always rethink any multi-output piece of digital logic as a collection of individual pieces of digital logic that produce single bits of output. Now these are going to be equivalent to things like an AND gate, which performs the logical AND function, which you might be familiar with if you recall from your discrete mathematics course, performing similarly NAND operations, OR operations, exclusive ORs, and inversions, just to name a few. Now, if we take multiple gates and put them together, we can create a single bit of storage that stores a 0 or 1. And then that 0 or 1 is fed down the pipeline to the next set of gates as input, or is fed out of the machine as output. If we have a collection of bits at the digital logic layer, each of which is based on multiple gates, if we have a collection of bits, we typically store those multi-bit values in something called registers. Now, a register is just a fancy name for a piece of memory that is very fast because it's directly inside the CPUs of our machines. And so because of the physical distance involved from getting from the registers to the CPU very close to 0, these things are very fast to store data to and very fast to retrieve data from. And these registers are, generally speaking, always a power of 2 in size in terms of bits. So we'll have 8-bit registers, 16-bit registers, 32-bit registers, 64-bit registers, and so on as time progresses. The layer above digital logic is the microarchitecture layer. Now, this is grossly simplified, but it gets the primary points across. At the microarchitecture layer, we're most concerned with how do we take information that is stored here in the register file, the register file being just a collection of individual registers. How do we get information from the register file over to the arithmetic logic unit so that some arithmetic or Boolean logic can be applied to that data? And then how do we take the result of that and get it back into the register file for some greater use later? Right? So this is the primary purpose of the microarchitecture. And that path that connects the register file and the ALU is called the data path. And this data path can be either hardware or software controlled. And throughout history, it's sort of gone back and forth between the two. And if it's software controlled, we will call the software that controls it a microprogram. Now, also, what the microarchitecture is in charge of is the execution loop of our software. So within the CPU, we are going to be acquiring register after register of information, not only related to the data that our program wants to process, but for the instructions of the program itself. So a primary function of the microarchitecture layer is to fetch from memory the binary for the next instruction that we're going to execute, which is shown here as fetch. So we fetch from memory the instruction we're going to be executing. That's just a collection of zeros and ones, and it's brought into a special purpose register here in the register file. Then that value has to be decoded. So the ones and zeros are reinterpreted to mean whatever they were meant to be: addition, subtraction, multiplication, some kind of comparison, or a piece of Boolean logic. That is decoding. A part of that decoding is not just figuring out what instruction, but what are the parameters for that particular instruction? Which values should be compared? What number should we add to this other variable? Those kinds of things. That's what the decode stage does for us. And then the final of the basic three stages that we talk about is the execute stage. So first we fetch the instruction we're going to run. Then we figured out what that instruction is, decoded it, along with what its parameters are. Once we have all that information, we can execute the instruction. So at this point, we're basically performing the addition, performing the logic or the comparison, or whatever it may be. The layer above the microarchitecture is the instruction set architecture. Now, at this level, we are basically exposing what the programmer level instructions are to the lowest level system software we can write. So here we have instructions like addition, subtraction, comparison, loading values from memory, storing values to memory, jumping off to some other part of the code to run it, jumping back from that code to continue where we left off, those kinds of things. At this level, we're not talking about big programming concepts. We're talking about very tiny operations that can be performed with minimal pieces of digital logic. So effectively firing off a small portion of the CPU's physical hardware. And that allows us to create a system that has very few, in general, individual operations that it can perform, but the selection of those operations is done very carefully so that higher level languages can use many of those instructions together to synthesize some higher level function, like, say, Pythagorean theorem or something of this sort, or raising the volume on the audio. Right. Now, each of these instructions at this level are sort of the raw instructions that the hardware is set up to do. At least generally that's the way I think about it. And so when we say that there's an instruction for adding two values, what we really mean is there is some binary, some zeros and ones, that represent, when entered into the computer, the act of adding some particular two values together. So these are effectively still very, very low level. Now, they may not all be implemented directly in hardware. So an example of this may be the introduction of an increment instruction. So we might have a piece of hardware, one set of digital logic that performs the addition of two values. And then we find very often in code that we need to increment a loop counter by 1. Well, instead of making some separate piece of hardware that increments by 1, which is really addition with 1 as a parameter, we can provide the binary code that makes it appear that increment is a standalone instruction, but then behind the scenes, the actual execution of the increment instruction might be done synthesized by a addition of two values instruction, where one of the instructions, or one of the addition of two values, where one of the parameters was replaced with a 1 automatically. Right? And so we have increment. But we can also potentially provide instructions that don't physically exist on the hardware, but are already synthesized by a number of the actual core instructions of the machines. All of this is exposed at this level to the system programmers above us. When we program in these multiple layers, again, we're focused on developing code in these high-level languages, and then we push that code through a compiler suite of some variety, and out of there comes either some low-level language code that we might want to investigate, like assembly language, or more often a executable binary that consists of the machine language of the actual architecture. And that's the thing that the computer itself wants to eat, right, is the machine language. And by programming in multiple layers, again, we are separating the burden of thought. When we write in the high-level language, we get to focus the developer's mind on the problem in its abstract form that matters to humans, not in terms of how many low-level additions or which subcircuits need to be fired in order for that higher-level concept to manifest. So that separation into layers, even at the software level, is very important for us. Then we introduce operating systems above this. So typically no one writes software directly on top of the bare metal and its exposed instruction set architecture unless we're developing very low-level embedded systems. And these would be very low-level. Most even modern embedded systems today have the capability to run at least some kind of small operating environment that'll give us as developers quite an advantage for releasing defect-free products in shorter periods of time, increasing our return on investment. So what the operating system does is it abstracts system components. So at those lower levels, we have the physical hardware that provides the mechanisms for networking, for sound, for video, and other such business. Now, we also have high-level concepts that are part of the system, like windowing. So you're watching this video probably inside the frame of some window, and your operating system is controlling that window, so that if you were to relocate the window as a user, no software written by the person who wrote that application is going to have to concern themselves with the fact that there is a new physical location in the video buffer that needs to have these pixels being rendered to it. All of that is managed directly by our operating system because it abstracts away those system components for us. Now this is super critical. Now windowing is an easy enough concept to just jump to and say, oh yeah, I don't want to have to write all the code that manages the window. But you need to internalize that ant and swarm concept. There's lots and lots and lots of teeny tiny little things going on inside your computer all the time to get us the robust experience that we've become accustomed to culturally. I want to focus on sound for just a minute here, just to give you a deeper idea of that. So the basic way that sound works in a system is someone would, and think about this if we had to control it yourself, right? That's the point here. So the basic way the sound is working is we need a particular tone to play. And so a digital signal, let's say a 1, needs to get put on a particular wire, and that wire gets routed to a speaker. And then the cone of that speaker kind of goes out a little. You've seen these things where speakers are bouncing in and out, when they've got a lot of bass. This is the concept we're talking about. That speaker is going to go out just a little bit. And when it does, it makes the air in the room a bit tighter. It compresses everything, right? So everything's gotten a little bit tighter, and the compression of that air puts a little more stress on our eardrum. And then in a tiny period of time afterwards, we're going to change that signal to its opposite form, let's say a 0, right? And suddenly that cone will say come back, right? Or whatever the filament may be. It'll come back and it'll decompress the air in the room just a little, relieving pressure on our ear. Now if it just went in and then back out one time, we wouldn't even perceive this as humans, right? In order for us to even hear that there's a tone, some code somewhere is going to have to make sure that code goes out and then back in, and then out and then back in, and out and in, and out and in, exactly the right number of times at the right rate so that the human ear hears something like middle A. So if we're doing middle A, I think that means all of that would have had to have happened 440 times in a second. And maybe that middle A is part of a sound effect in a video game that we're playing, which is, of course, a big piece of software. The idea is it's not just that we need to make sure that that speaker goes in and out and in and out 440 times a second forever. It needs to do it for a brief moment as part of a note in a grander scheme of sound where the frequency is changing all the time, but we have to keep moving that speaker in and out correctly or the human perceives something other than what we meant. At the same time, we have to allow that user to move the mouse around, right? And to update graphics on the screen so that the complete experience is enjoyable. And that's a gargantuan task if we want to break that down into the level of the ISA, the instruction set architecture. If we wanted to make all that happen in our code ourselves in terms of things like adding one and occasionally comparing data and jumping somewhere else in the code, we would find this virtually impossible to do without, one, taking an incredible amount of time, two, writing amazing amounts of code, three, introducing by sheer probability of typing the wrong thing because we've typed so much, we can introduce defects, and then four, we effectively super decrease our return on investment. Now that's not to say I don't want you to consider writing low-level code, but low-level code should be left to rare occasions, and instead we want to focus on that higher-level code. And operating systems, even though they're not a part of our compiler or a direct component of the hardware that we run our programs on, operating systems provide us as programmers an additional layer of abstraction that makes our lives much more convenient. Right? And in doing this, effectively what happens is the operating system is providing a kind of a virtual machine on top of the ISA, because the ISA standalone, while we could program in that, doesn't give us enough flexibility. Right? And it doesn't know about the specific network card that we've attached to that particular computer, but the operating system does. So the operating system can expose through various APIs mechanisms for the higher level programmer to interface with, say, the particular network card that's active right now on that particular piece of hardware that we're running on. And if all this is done well, then we effectively could take that code and put it on a different operating system that's running on a different piece of physical hardware, or even a different version of the same operating system. And that's very powerful. So with all that power, everything gets easy, right? This is the note I have at the bottom of the slide. Everything gets easy. Well, of course not. But it gets easier. It allows us to focus as software developers our attention on the higher level problem at hand and not be forced to move in and out of high level and low level details constantly as we architect our code, design our solutions, and then implement them. So, why use multi-layered computers? So we've hit this over and over in this short video, and I'm going to remind us again. We want to abstract or separate the tasks involved in working with the hardware and working with the high-level software concepts. We want multi-layered systems because we want multiple layers to make the design of the hardware computer systems effective and efficient so that we can improve hardware systems quickly over time. But we want to go further and separate away the logical operations that are going to be performed by our programs. We want to provide that other layer for software developers to do different things in a generic fashion rather than in a fashion directly related to the hardware that they will be running on. And that gives us great productivity. Now there's an interesting side effect, of course, of breaking things into multiple layers. And for right now, we'll just focus here at the end on the separation of hardware and software. So listed on this slide, I identify that hardware is effectively this stuff that is tangible. And that means you can touch it. So it is easy. It's typically built on your electronics or on some kind of mechanics. Now, I don't mean to say gears and such, but you know, there could be, for specialized systems, control system, things like relays, which have physical switching involved. So that's the hardware side. But logically equivalent, if you recall a previous lecture, logically equivalent to that hardware is software. Software that can do the same thing that that hardware does. And that's what we do when we program. We write it out one way. It gets translated into machine language so that the hardware can perform that same set of operations. But what's unique about software, first and foremost, is that it's intangible. Now I have notes here that it's also algorithmic and transferable, and while that is true, I'm going to completely skip over this entirely. I want to end this presentation by talking about one of the interesting side effects of software being intangible. This means that it doesn't have a real physical form. Now, obviously, the bits must exist somewhere if they're going to be run, and so they may just exist in one location as a form in forms of voltage or something. You might say, oh, well, the software exists on a CD or a USB key, something like this. Yeah, okay, those CDs and those keys exist, and they do have zeros and ones on them effectively. That could be interpreted as the particular software we want. But what's really important to understand here is that software itself, the concept of the actions that solve the problem, are not actually tangible. And one of the great benefits of that is duplication. So I have my iPhone here. This is a piece of hardware, and if you wanted a copy of it, you can, right? You could steal it from me, and then I don't have it anymore, and you have it. But you can't copy it. But we can with software, and we can with data, because it isn't tangible. Right? Now, that has obvious benefits. So if we're developing software for a company and we want to deploy it to all the systems, it's not about manufacturing a bunch of physical devices that have the information that we can then put into everyone's computers. We can just distribute the software electronically, intangibly. But a negative side effect of that relates to security. Right? And I think this is an important subject that we sometimes fail to focus on. So let's talk about a negative consequence of intangibility as it relates to security. And we'll do it by thinking about things that are tangible in the past. So say someone nefarious wants to steal your mail and use it for some filthy purpose. Well, in the old days, you know, maybe they hid behind your trash cans or behind a van or something like that and waited for you to go to work. And then they might sneak up when no one was looking to the mailbox after the postman came, open the mailbox and take your letters. But then they have to physically get out of your vicinity to successfully escape with these acquired letters. And if they wanted to sell that information to somebody else, they would have to find that person, generally speaking, physically, and then convey the information somehow. So they'd have to take the time to talk about it or whatever it might be. The modern world is very different. No one needs to hide anywhere to steal your information. If they can get access to it in an intangible form, it can be acquired almost instantly. Worse, if that individual wanted to make that information accessible to others, they could distribute it intangibly in virtually an instant. So there is bad with the good, and so we must be conscious of those kinds of things and understand the implications that come along with all those benefits of breaking a computer system into multiple layers. Now, I hope you enjoyed this talk about multi-layered systems, and I look forward to seeing you in the next video.